All right. Good morning, everybody. Happy Tuesday or Physics Monday. You know, all we really have in here is Physics Monday and Physics Friday, right? A first class of the week and a last class of the week. Sort of how it works. So we have a good day and a bad day, and I'm sleepy today. Anybody with me? Yeah, sleepy. So maybe I should just open a book or something, and we'll turn the lights down, and I'll read a chapter, and we'll all just kind of have a little bedtime story, and just not even worry about that exam that's coming up. We'll just kind of forget about that, let our cares drift away as we sleep for an hour and 15 minutes. Doesn't it sound fantastic? Yes?
I have a question.
Yeah.
Actually. So, one of my friends is in the 8 a.m. class, and I got word that the exam has been
Moved? Like to a new location?
like to a different,
Like outside? We're going to have it
we're no
outside?
longer doing it? No. Like
We're never going to have this exam.
Yeah, it's never gonna happen.
It's going away. I would like to move it to next Tuesday.
Yes, please.
Hold on just a second. I do need to know if there are like life-changing ramifications for anybody that's negative.
I would get sleepover next week.
Next Tuesday, and take all this week for reviewing.
Yes.
You have a question?
If you did that, that would be very nice because you would consolidate all my exams for this month into just 2 days.
That's nice or bad? It doesn't sound like a good thing necessarily.
But then you just you go into
You
exam
feel
and then you just stay.
Oh, you get an exam. Question in the back.
Well, I actually want also because of the fact that you may have midterm review and the problems you have for our chapter 5
Mhm.
those available so late in the game.
Yeah, I did.
So
That was pretty
I
late.
don't think I can go through all of them, memorizing the answers and processes entirely in just a couple of days.
Yeah.
Especially considering all the other classes I have.
Yeah.
There's just simply not enough time.
Also, I'm scheduled to give 4 exams this week, of which 1 is currently written. So you guys are stressed. I'm stressed in a different way. It's like the other side of the same coin. Next Tuesday would help you out and help me out as well. Yeah? Sounds good? We're on the same team? Yeah? Okay. If there's anybody out there who's being quiet and because like this is changing your life in some bad way, reach out to me. Okay? Talk to me after class or send me an email and we'll deal with your individual situation and try to be fair to you as well, whatever that may happen to be. Okay? Yes.
So does this mean we're gonna do a review on Thursday?
Mhm. Mm-hmm. So we're going to start this review today. I got about 45 minutes into class this morning, and my wheels started churning because I saw how far into the review we were and how much more that I still wanted to do. And I was just thinking as I was talking, is there any reason we couldn't do it next Tuesday? And I couldn't come up with anything. So I'd like to cover as much of this review file as I can and also do a couple of problems from that force document that I gave you with the extra problems. And I'll probably do those on Thursday, okay? So we'll make it through a little bit of this today. We'll finish it up on Thursday, whatever we can. And then next Tuesday, don't think I'm going to move it again. I can't move it again. It'll be too late then. Yeah.
Can we have an answer key for the results that you sent us last week?
Yes. So I will do 2 things. You will get answers to all of these in the post-lecture file. Let me hold a few days on the other ones because there's this temptation if I give you solutions and problems, everyone like wants to read solutions, and it's nice if it's like kind of you're forced to sit with them for a couple of days before the solutions are available. So, but I will make it available to you a little later. Okay? All right, so let's get started. I received many emails with many questions of things you guys wanted worked during a review, which led to this document being so long, which led to us no way being able to finish all that in one class. So I have prioritized a little bit. I put up front the problems that I felt like we needed to have a look at and that would satisfy the most number of questions that were out there. And then there are some duplicates, not the same problem, but the same problem type, that I put a little later that we'll do Thursday, just sort of if there's time. Okay. So I'm sorry I can't necessarily answer everybody's question, but if we don't get to yours, send me an email. I can send you a personalized solution or something. I don't know. Yes. What's that?
I have a question about the
Yeah.
thing. So, say we could bring like a one sheet of like kind of like a cheat sheet or formula sheet. I read in the email or I forgot where, but you said there's an equation sheet provided.
Mm-hmm.
So we could just kind of like write our own solution and the equation provided.
You can write on the equation sheet and bring that as your page, but you don't get like a second blank page in addition to that. If you want the page that you write on to be my equation sheet, that's totally fine. Okay? Yeah.
Wait, so I'm confused now. So you're giving us an equation sheet,
I'm giving you an equation sheet,
and then we can also do notes.
and then you get a page of your own notes.
Okay.
You can merge those into one, but
Like, can we kind of get that early so we know, like,
it is already posted.
when it's posted? I just missed it.
It is posted.
Cool.
Yep.
Never mind. Just kidding.
Unless I forgot this class for some reason, which could have happened. Yes, it should be there.
The equation sheet is posted on our end?
Mhm.
Oh, okay, I couldn't find it there, I just have it in the one email you sent.
I created a section just called Exam 1 or something after the first 5 chapters. There should be the equation sheet there, and I think this file. And I think that's
Okay,
it.
yeah, I haven't seen that.
Okay.
Okay, thank you.
Take a look, and if it turns out that I'm wrong and I posted it in one section, not the other, which sometimes happens, please let me know, and I'll fix that. Okay? So, let's see. Vector components. Someone wanted me to sort of step back and quit skipping over the details, which I've been doing, and just make sure that we're all on the same page about how to calculate vector components. So I'm going to do one sort of quick made-up example and actually step through the trig of each step this first time. And then on the next problem, there's a little bit more of that. I'll probably do it twice just to make sure that we're all on board with vector components. So let's say that we had an XY coordinate system, first of all. And let's say that we are given a vector. Well, let me first of all put plus x plus y. And maybe the vector we are given is 7 meters at 32 degrees west of north. So I'm going to make the assumption that north, south, east, west sort of just, that's not north, what's wrong with me? Sort of maps onto our XY plane just like you might expect. And you might find a number of different ways that a particular angle is described. There should be enough information for you to figure out where in the XY plane this thing is located. So when we say west of north, we're saying that we start in the north direction, and then we're going to go 32 degrees over toward the west direction, to the west side of north. Okay? So that means the vector is going to live like right here. So it has a length 7, and this angle is 32 degrees. Okay? Good so far?
What is the M?
Just meters. I just gave it some units. So maybe this is a displacement vector. Okay? So let's see. If we want to break this into x and y components, I'm going to draw 2 other vectors, head to tail, such that they would add graphically to give me that original vector in the back.
I was a little confused in the words that what it means like west of north, like especially when I'm graphing them.
Yeah,
So does it mean like northwest or?
that's basically what it's saying. Let me write out the words that I used. This is like, we'll say to the west side of north. So if north is straight up this way and west is over here, somewhere over here is the west side of north. Somewhere over here would be the east side of north. And you can imagine we could have the south side of east and the north side of east, and we could go to either side of any of my axes. I will try to typically in an exam avoid notation that seems I don't know, a little bit arbitrary and sort of out there a little bit. Maybe I'll just say to the positive side of the x-axis or something along those lines. I'll try to be a little more straightforward with it. Okay? So looking at these two vectors that I drew in pinkish purple, okay, they're head to tail, so they can be added back together to give me the original hypotenuse, okay? So think of those two pinkish purple vectors as literally the things that are inside, the parts that make up the original 7-meter vector, okay? So I can take apart the 7 and I find those two vectors. I can put those back together and I get the 7 again, okay? So looking at this, we could say that this particular vector is the y component. It's pointing in the y direction. And this one is parallel to the x-axis, so we'll call that the x component. And then what you might do to determine which trig function to use is think about what you have and what you're looking for. So for instance, I have this angle, I have the hypotenuse, and maybe I'm looking for the x component. So in green here, these are the 3 things that have to be in the trig function I'm going to use. So I've got an angle, I've got a hypotenuse, and I've got the opposite side from that angle. Opposite, hypotenuse, angle. Opposite, hypotenuse. That sounds a whole lot like the sine function. So the sine of theta is opposite over hypotenuse, which in this particular situation translates to sine of 32 equals my x component over 7. Look at what you have, what you're looking for. That's going to match one trig function. Sometimes you may have an overabundance of what you need, and you'll be like, oh, I could use this trig function or this trig function, and it would be just fine. Okay? So if I rearrange this, the x component is 7 times the sine of 32. And someone needs to tell me that number because I have no idea what it is. Although it'd be pretty awesome to like have the trig functions memorized.
0.5299.
Who, what, huh?
0.529. Well, sine 32 is 0.5299
Times 7,
3.709.
3.709, 3.71. Okay? Now, which direction is that vector pointing? To the west, which is the negative x direction. So I need to go back in and put a negative in for that vector. Okay? I found the length of that side of the triangle. Now I need to reinterpret it as a vector in the diagram and be like, oh, it's pointing left, that's negative. Okay? If we're going to find the y component, let's just switch to another terribly clashing color because everything up there is looking kind of horrendous at this point, don't you think? Maybe a little bit? Why not? Let's go to blue. We haven't used blue yet. So I still know that I have 7 and I have the 32. And now maybe I'm looking for the y component. So I've got the hypotenuse, I've got the angle, and I've got the adjacent side for that angle. Adjacent, hypotenuse, angle. Adjacent, hypotenuse, angle. That's sounding like a cosine. So cosine theta is adjacent over the hypotenuse, which in this context is cosine 32 equals the y component over 7. If you need or just want to take these steps every time you find components, there's nothing wrong with that. Yes?
Could you just use the Pythagorean?
You could, now that we have 2 legs, and that are 2 sides. We have a leg and a hypotenuse, that's still good. Yeah. Once we found the first one of these, then you've got multiple options going forward. So let's see. Y component equals 7 cosine 32, which gives us what? 5.94. Okay. I'll accept that. I have no idea. Why not? It's pointing up to the north. That's in the positive direction. So we'll go ahead and leave that as positive. Those are the two component parts that make up the original vector 7 at 32 degrees west of 0. Okay? Take the extra steps eventually. You do enough of them where you're just like, well, this one's going to be sine, this one's going to be cosine, and you kind of are able to skip over that a little bit. Yes?
So how do you know which is to point the arrows?
It's the way that they add to give me the original vector. They need to be head to tail, and they start at the origin such that the hypotenuse is going to be the one that I'm breaking apart. So if you reinterpret this as a displacement vector, if I want to get from the origin out to the end of the 7 meter vector, the way I get there is by going up and going to the left. That tells you which way to go. Okay. Can I confess something to everybody? Just to make you feel better? It took me a long time before I got comfortable just straight up writing something cosine theta, something sine theta. Okay? I spent many years like doing the trig because it just bothered me and I wanted to make sure that I got it right. So don't hesitate at all to take these extra steps. It's not a problem. Yes?
I don't get what you're saying when you say that those two vectors add units to hypotenuse, because like mathematically, when it adds units to hypotenuse, so can you explain?
Mathematically, they do add to make the hypotenuse because they're vectors. Using regular arithmetic, you're right that they don't.
Okay.
But I can't use regular arithmetic because they have direction.
Okay.
So, for instance, what we are saying is that if it is 7 meters from here to the trash poster, which, yay, trash poster once again, like I can go 7 meters by going directly there, or I can go, let's see, 5.94 meters this way, and then 3.71 meters this way, and get there. Those add as vectors to give me this result. If I just add those two numbers together, you're right, I'm going to get a bigger number than 7.
So they
But-
both get you to the same place.
They get you to the same place. The addition works. Yeah, over here.
So adding vectors when they make a right triangle is just as simple as doing the Pythagorean theorem or doing trigonometry. But what about,
Yep.
were you ever asked to add vectors that don't make a right triangle?
Yes, and when you do, you break it up into right triangle parts. So it always results in that.
So how would you do that?
So for instance, if we had like a vector that was like this, and I wanted to add it to a vector that was, I don't know, like that. Okay? I would, for both of those, say, ooh, let's see, what are the components that make up this one, right? And it goes that way some and this way some. I'd find that.
Okay.
And then separately, I'd say, let's do this again. The second one is kind of going down this way. I would find the components that make up that one, and then add up the components.
Out of the length.
Add up the x parts, and add up the y parts.
What?
Next example will
No.
answer your question. Okay? So in this particular case, like you can see these two vectors right here, they are not perpendicular to each other. Okay? If we read this, it's got a spelunker. Who doesn't want to be a spelunker? Has anybody spelunked? No spelunkers. People who crawl in caves? No? Okay, never mind. Let's see. So we go some different vectors here. This person goes 75 meters north, 250 meters east, then 116 meters at an angle 30 degrees north of east, and then 179 south. Okay? So a bunch of different motions. We're going one direction, then another direction, and then off some other direction, and then another direction. And we're trying to see what the result of all that is. So when it says down here at the bottom, find the resultant displacement, all that means is literally add them all up. Okay? We're just adding all the individual motions to see where we are from where we started as a result of all that. Notice it also says that diagram is not to scale in any way, so don't get the idea it's like, oh, well, I ended up like at the, just like over to the side from where I started. Like, we don't really know where we end up until we do the math, okay? So, let's do this. Let me label these 4 vectors. I'm gonna call this one A, and this one B, and this one C, and this one D. And then, whoa, that was a big eraser I had. I need to scale that back the next time. Okay? A, B, C, D. We're going to express all of them, A, B, C, and D, in terms of X and Y components. That's the only way that we know how to add vectors, okay? So whether they happen to already be perpendicular, or they're off at some weird angle, or if all of them were like, maybe it wasn't like this, and it was like, wee, like over this way, and then like over that way, and then down here, and then over here, and then down there, and over here, and up here, like this, the procedure's exactly the same, okay? It's just that that would be a whole lot more work, and would be a little painful, okay? So we're not going to do that. Yo, make it go away. There we go, okay? So here's what I want to do. We're going to write out vector A, and B, and C, and D, and we are literally going to add them. Breaking them into components is what allows us to get from like, oh, I can't just add the numbers to, oh, I can use regular arithmetic and add the numbers. It allows us to like step away from the vectors a little bit. So if I were to write out vector A in terms of an X part and a Y part, like how much I have to go in the X direction and how much I have to go in the Y direction for that to occur, well, take a look at what it says for this first vector, 75 meters north. North, we've determined, is positive Y. If I just go straight north, I'm not going east or west at all. I'm not going in the X direction. So that means, yeah, this is 75, and this one's just 0, okay? So we can plug in 0 in the X direction and positive 75 meters in the Y direction. Okay, maybe. No, I don't see any hands. The second part is just as easy. 250 meters east is my B vector. That means totally in the positive X direction, but nothing in the Y direction. So I can write that as 250 in the X direction plus 0. C, I'm going to skip for a second. Okay, your question?
Why isn't the Y for B 75 if she went 75 north and then east? Or is it
75 north. So the 75 north is here.
Yeah.
And then the 250 east is there. But those are 2 different separate motions. Okay? So if we were to go back and label them here, like this is A and this is B. Okay? Let's jump down to D. D says 179 south. South is which direction? Negative Y, right? So if I were to put that down here, this is minus 175 in the Y direction and none in the X direction. So they left it without too much work for 3 of the motions, okay? For C, we could sort of zoom in a little bit on that vector if we wanted to, and imagine that the equivalent or the components of vector C would be the same as going to the east some and then going to the north some. So some in the positive X direction, some in the positive Y direction is the exact same thing. So this is the X component of C, and this one is the Y component of C. If I want to find the Y component of C, notice I'm looking for this one, and I know this one and I know that one. Okay, so that's opposite, hypotenuse, and angle. That means I'm going to use the sine function. So sine of theta is the opposite side over the hypotenuse. The opposite side over the hypotenuse. And I will need help with some numbers once again. So let's transition that over into the numbers they gave us. So sine of, what was the angle? 30 degrees equals cy over 116. So cy is 116 sine 30. Somebody's going to tell me what that number is. Okay, maybe not. That's fine too.
$58.
58? Just 58?
Yeah.
Just 58?
Yeah, because sine 30 is 1.
Okay, that sounds great then. 58. 58 in the positive direction. Okay, so let's go plug that in down here. Plus 58 in the y direction. If I want to find the other one, so let's go to a different color like this one. If I want to find CX, and I know the hypotenuse and I know the angle, well, that's the adjacent side, hypotenuse and angle. That's going to be the cosine is the adjacent side over C. My apologies, that's a little hard to see, but when you look at the file later, it'll be lovely. You'll like it so much. So CX over C, in terms of what we have, that is the cosine of 30 equals CX over 116. So CX is 116 cosine 30, which is 105?
100.45.
100.45. I'm just going to make it 0.5. Perfect. Thank you. And that is in the positive direction, so down here we will say 100.5. And everything is color coded, so you know where those numbers came from above. You got that. I'm going to become a color matching addict now. As you all flip your little pens. Match the colors. I hear you out there. 4 color pens. So once we've done this, and keep in mind, 3 of these vectors, they tried to make easy for us by making them not be at an angle or anything. We could have 4 vectors that were like this, that were off at some weird angle. We would do the exact same thing. Find out how much you have to go in the x and the y direction to get that particular vector, okay? Once we've broken all these up, this turns into regular arithmetic, okay? So I can literally just say 0 plus 250 plus 100.5 plus 0 is going to give me the x component of the sum. So down here at the bottom, let's call this R for resultant, okay? So 250 plus 100.5 is 350.5 in the x direction. And then we will add up the other column to find the y component, okay? So 75 plus 58 minus 175. Yes.
I think it should be 179.
179? It is 179 up there. How'd that happen? Who knows? 179. Thank you. So what's this going to give us? Negative 46. Negative 49. Oh, now 75 plus 58 minus 179. 46. 46? 46. Okay. So this is close to the answer. I want to stop here for a second, though, and think about what this result is telling me. Okay? Again, imagine the motion that they're describing. Okay? Let's just say that to the front of the classroom is north. So that's north, this is east. Okay? We're saying that we go this way some, and then we turn this way and go this way some, and then we turn off at this angle and go this way some, and then we turn all the way south and go back here some, okay? You can see that I've moved from over there to over here some distance, okay? That would be in the east direction, in the X direction. Well, notice, this is how much that I've moved from here to over there, all right? I've moved 350.5 meters is what we're saying, all right? And if you think about those motions that I had, the ones where I went straight toward the front and straight toward the back, that didn't contribute at all to me going sideways. It was only when I turned this way and also when I went at some angle that I had some motion sideways across the classroom. And we see that reflected because only these two have a component in that direction, okay? This is telling me how much I moved front to back of the room. It's telling me that the result is I end up 46 meters behind where I was. So if I started here and I went there, at an angle, and then back, apparently I end back here somewhere, okay? I've moved backwards a little bit. Well, again, look at what contributed to that. This one said I went toward the front of the classroom. This one was me going directly toward the back. This one was me going toward the front of the classroom a little bit because I was at an angle. Those things add to tell me how much I've moved front and back in the classroom, okay? So if we were to go over here and draw that, let's see. No, let's not do that yet. We are saying that basically it looks like this for real. We started here, and then went over here, and then went up some, and then went back down, and ended up sort of down there. Okay? So when they say that diagram wasn't drawn to scale, they were very much right. Okay? So let me redraw that last vector and say that this is R. It is the sum of motion for A, and then motion for B, and then C, and then D. When I add all those vectors together, I'm saying that I moved from here, and now I'm over there. I moved from here to back there somewhere. Okay, that's the result of all of that motion. All right? Are we still doing okay? This fits together a little bit, maybe. Well, now maybe I want to find, like, well, how far away am I from where I started? Like, all this, like, I'm wandering all over the place, but, like, maybe I'm, like, right next door to where I started, or maybe I'm forever away. I need to find out the length of this vector to actually find out how far away I am. To do that, let's just put it on its own little coordinate system. Okay? Notice, it's saying 350 in the x direction and negative 46 in the y direction, which means I can take this vector and say that it's the same thing as 350 this way, and then down that way, 46. That should have been a 5 back there. I got all caught up in the 46 and made it a decimal. There we go, 350.5, and that way 46. If I want to find that hypotenuse, that's the Pythagorean theorem. We know the two legs, we're looking for the hypotenuse. So if I want to find this, it's the square root of 350 squared, 0.5 squared, plus 46 squared. Okay? So this tells me that I am 353.47 meters away from where I started as the bird flies, if you want to think about it that way. Just on a direct line, if there was a way to get there. But we're crawling around in a cave, so there's probably no direct way for me to get back. I've got to crawl through all those crazy tunnels again. Okay? If I want to find this angle, like I'm 353 meters away, in what direction? So we could find theta by using the inverse tangent, because tangent is opposite over adjacent, opposite over adjacent. So I'm going to use that trig function, but use it backwards using the inverse, and it gives me the angle instead. And you would get 7.5 degrees or so, and that is south of east. So it's not east, it's to the south side of it. The negative in here? No, because we're really just solving a triangle at this point. You could put the negative in, and I think it would give you negative 7.5 degrees, which really means the same thing. It's not a serious matter either way. That is a delightful problem that explains a lot of different things about vector components and addition and all of that sort of stuff. And I hope it makes a little bit of sense. Yeah, a couple of these problems we have today are like these big, like, oh, that was a lot, but it also explains a lot at the same time. Your question.
So from this question, you're asking for all of that too, like not just that, but like all of that too.
Yeah.
When you say the result, okay.
Yeah. Unless it were to specify, find the components of the resultant displacement, and this would be the components of it. But this doesn't tell me a whole lot. It doesn't really tell me actually what my displacement is. Yes.
So the resultant displacement is that final answer we got?
Yes. So that number at that angle is the final displacement. What was that? Yeah.
So it's just the magnitude?
This is the magnitude of the displacement, and this gives us our direction of displacement. Those two things together give us the full vector. Hello, people in the hallway. They sound like they want to come in, don't you think? We should invite them in. They sound like they're like, we don't know where to go. We need a class. Okay, maybe they don't want to be in here. It's hot in here. Isn't it terrible? What's the deal? Are all the windows open now? They are. Ugh. Did I prop this open? Did that help at all last time? Did a breeze go through? It's not going to work. We can invite the people and we can do this. Should I open the door really fast and scare them?
Yeah.
There could be someone standing right on the other side of the door, you know. And then I'd be like, you know, sued for assault or something. They didn't look like they wanted to join us. I didn't ask. All right, so let's move on a little bit. Let's see. Looking at our time, trying to decide what I want to do next. Yes, let's make time to do this. So, motion graphs. Just in general, let me go over the theory behind it all first, and then I'm going to answer one of the questions that there have been a lot of questions about, and hopefully once we talk through the theory again, it will assist. All right, so motion graphs. We've got position versus time graphs. So this could be X or Y as position, either one, or Z or R, or whatever you wanted to use. We'll refer to X most of the time. I think that air is moving a little bit, at least across the front of the classroom. If you want to prop the one open in the back, that's totally fine. Or just take one of your classmates and use them to just wedge them in the door. If you can't find a chair, that's fine, I don't care. So we've also got velocity versus time. I would love to say something like that one time and someone to actually take me up on my ridiculousness, but it never happens. Velocity versus time, and we'll briefly mention acceleration versus time, although there's not much that we're going to do with that. So, don't forget a couple of different things. First of all, for position versus time, the slope of the graph tells me what? Tells me velocity. Now, if that slope is the slope of a tangent line to something that's curved, it's telling me the velocity at that instant. If that is the slope between like 2 points that are separated, well then it's telling me an average between those 2 points, okay? But the rule is that slope is telling you about the velocity. When I get down to the velocity graph, what does the slope there tell me about? Excellent, so that is the acceleration. Now, a couple of different things on the XY graph, the X versus T graph. So if I were to say, actually put some points on here, let me just kind of put a few in. Points on that graph are literally telling me where the object is, okay? So if this point corresponds to a particular time, I would say at that time, the object is located at whatever number that is on the x-axis. That is where they are. So if I have positive values at the top, those are positive locations. The ones where I have negatives down there below the t-axis, those are negative locations. They're actually defining different points. If I were to connect those dots, just as an example, Remember, the slope there is telling me the velocity. Is that slope positive or negative?
Negative.
That is a negative slope. This is a negative slope. And if it's telling me velocity, that means I have a negative velocity. Which means that I literally have motion in the negative x direction. Of course, positive slope would be exactly backwards, okay? So I don't think I need to write that. I don't think I want to write that. It's a lot more things to write than I want to, okay? So let's make sure that our interpretation of the slope matches the points on the graph. So you might imagine that I'm starting at some location that is positive. So let's pretend that toward the door is the positive direction, and maybe 0 is like right here. 0, positive, okay? So I need to start over here somewhere. And then where do I go next? You're like, go that way. The door's already open. I gotta go this way, right? I'm getting closer and closer to 0. So I'm going this direction. Eventually I'm going to get to the point where it actually is 0, right? And then I'm gonna go to some negative positions after that. Okay, so I move from there through 0 over to here. That is telling me what each of these points mean. Now think about the motion that just happened. The entire time I was moving that direction, which is the negative direction. I had velocity in the negative direction, which corresponds to the slope. Okay? So the points on the graph agree with what our interpretation of the slope is. I'm moving from here to here at a constant velocity in the negative direction. Do you feel okay with position versus time? I think typically people do. It's this other one causes problems. Velocity versus time. So I'm going to write this time. If I have a positive slope, we might have to close it. That gives me a positive acceleration, which doesn't have anything to do with which way I'm moving. It has to do with which way I'm being changed, which way I'm being influenced. So in other words, a positive acceleration means there is an influence in the positive x direction. And negative slope would be the opposite. I will write it out this time because it's a little more confusing. Positive slope means positive acceleration, which means there is some type of influence on my motion that points in the x direction, positive x direction. Negative, same thing, but the influence is in the negative x direction. We have now learned at this point what that influence is. It's called a force, right? Something is pulling or pushing me in a certain direction. So, if we were to draw the exact same line, let's just look at something that's identical. The interpretation is different because I'm plotting different things. Think about what the points on the graph mean. Right here is a positive value for the velocity. This is a positive value for the velocity. This is a positive value. This is positive, this is positive, this is positive, this is positive, this is 0. This is negative, this is negative, this is negative. Okay? Positive velocities mean I'm moving in the positive direction. Negative velocities mean I'm moving in the negative direction. So, at this point, I have a velocity in the positive direction. That means I'm moving that way. What am I doing next? I'm still moving that way, but I have less velocity, right? And then the next instant, I'm still going that way, but less velocity, less velocity, less velocity, stop, right? So all of these are motion in the positive direction. Apparently I start with a bunch of motion, so it's like, ah! And then I slow down, and at some point, stop. And then my velocities become negative, which means that's motion in the other direction. And then it's getting more negative, which means I'm going faster and faster. Okay? These are motion in the positive direction. These are motion in the negative direction. Okay? So this is all positive velocity. This is all negative velocity. This is slowing down. this is speeding up. The magnitudes are becoming less, and then the magnitudes are becoming greater. So slowing down and then speeding up. Even though it's just one straight line. It's just weird. Is this slope positive or negative? You told me it was negative up there, so this is negative 2, which means negative slope, I have an influence in the negative direction. The negative direction is that way. That means one of you terribly mean people is up here pushing me that direction while I'm trying to walk that direction. Why would you do that? Right? So don't try to stop me. It's like, no, I'm running this way. And then you're like, oh, go that way. Go that way. So I try to fight it. I eventually stop. And then you turn me around and speed me up like this. The entire time, there's a negative slope because there's an influence that way, which changes my motion. Good? Good? We've got it, maybe a little bit. Let's look at this problem. Yeah. Yeah. So, now, if you've never seen this problem, what have you been doing? You need to be working on your homework. Okay? If you got halfway through and got stuck, I'm about to help you. If you solved it, this is an excellent review. Okay? Let me point out a couple of things first of all. Let's look at the graph itself. X, T, position versus time. Remember position versus time, the slope tells me velocity, okay? So let's look at the slope sort of everywhere and see what it's doing. You might imagine like right here at this point, I've got a slope that's kind of up, right? It's positive. And then I go over here and it's a little bit flatter. And then I get here and it's kind of about the same. And then up here it gets a little flatter. And at the top it's perfectly flat. And then it goes around here and all of a sudden I feel like I'm just sort of like shading things in, having fun. And it gets steeper and it's negative now. And then we can go here and you can see it kind of starts to flatten out. It gets flat at the bottom. And then switches back positive and gets steep again. Think about every point what the slope of a tangent line would be doing, and that's telling you about the velocity at all of those points. Okay? Yes, 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 yes. So let's interpret the motion before we deal with any of that. So I start at the origin, wherever that is. Here's 0. Yay, I'm at the origin. We're going to say that way is positive. We're going to start with a positive velocity that's going to sort of mellow out, right? I start with a steep slope, and then it gets a little flatter, and then eventually goes all the way flat, okay? So this first motion is like me moving this way, and then moving a little slower, and then eventually slowing down and stopping. That gets me to the peak in that graph. Everybody see that? It's all positive velocity, but the magnitude is changing because the slope is changing. After that, you can see the slope becomes negative, which means, ooh, negative velocity. I'm going to go back this way. Well, it also just makes sense because my x values are going back down. Okay, so I'm going to go back closer to the origin. But now it's like I'm going to speed up in this direction, and I'm going to speed up and go faster and faster and pass the origin, and then once I pass the origin, start to slow down until it goes flat. And then we're going to turn around back this way and then speed up, and eventually I get back to the origin. Okay? Do you see that? See the motion and how the velocity is varying according to the slope. You're not saying anything. Do you exist? Or am I in a dream right now? That question didn't get answered. I must be in a dream. I need to look for something that seems out of the ordinary, like very out of the ordinary, where this couldn't be real life. You know what it is. I'll keep looking. So if I want to look at this now and find, look at A through G. These are all the exact same question, right? So let's just bunch all these together. They're all looking for the average velocity. So that means, yes, I'm going to use the slope. And the slope here is the change in x over the change in time, and well, that is the equation for average velocity. And let's just do that for one of these because it's terribly redundant to do that all of these times, and I'm sorry, I don't know why this particular question does that to you so many times. It's just life, right? So let's say I don't know, between 3 and 6. Let's do that one, okay? So going back up to our graph, actually I need to keep it large enough so that we can actually see all the numbers. Go bigger, there we go. Between 3 and 6, so at 3 seconds, my position is 20, and then over at 6 seconds, my position is 28. So we're going from 20 to 28 in 3 seconds, which means I can go back down here and write this as, get the right thing, x final minus x initial over t final minus t initial. That's 28 minus 20 over 6 minus 3. Okay? The ending time and the ending position, starting time and the starting position. So that is 8 over 3, which is 2.66, 2.67. That'll work.
Wait, so it's as simple as like as if it was a linear function.
Well, the homework is
8 over 3.
I don't think I'm honestly not sure. They may want the decimal. We are pretending it's linear between those 2 points because essentially what we're doing is going to this point and that point and drawing a straight line between them and finding the slope of that. That gives me the average velocity, and it literally averages all of these individual slopes at all of those points.
Okay, well, what about at a given point?
At a given point, we'll get there. Coming up, okay?
It's starting to like make me nervous because we're gonna get on the test.
It's the same, as you'll see in just a second, okay? So for A through G, that calculation is identical. Pick 2 points, find the slope of the line between those 2 points. In H, when is the particle momentarily at rest? Well, that's when the slope is equal to 0, right? So when the slope is equal to 0, V is equal to 0, and we see that happening 2 places. At t equals what? 6 seconds and 10 seconds. Okay? It goes momentarily flat at those 2 points. Which brings us to this question over here, which is what you really want to answer. Yes?
I have a question about that actually. So when it says momentarily at rest, do you just like knock off the edges? Like would you not include 0 and 12 even though it's coming to rest? Starting at rest.
We don't really know what happens at those other 2 times.
You can see it.
Is 8 seconds at 0 as well?
8 seconds is at position 0, but not slope 0. Okay? And dealing with at 0 and 12, there's a slope going into those points.
Oh wait, I see.
Yeah, can't be flat. Okay? Looking for other questions. No, nobody else out there. At what time is the particle moving in the forward direction? So that is a positive velocity, which means I need a positive slope with the fastest speed. Let's just say that that's when it's the steepest. When is it positive and the steepest? Think about all those individual little purple slopes that we could draw. It's positive everywhere except between 6 and 10. Everywhere else is positive. Of all those options, where is it steepest? Between 0 and 1 is one of the steepest. I would agree it's really steep there. And then it gets less steep, less steep, less steep. So for this part, that is definitely the steepest. Let's compare it to over here. It's flat, and then steeper, and steeper, and steeper. Which one's steeper, at 12 seconds or 0 seconds? Looks like 12 is increasing more rapidly. So our answer there is at 12 seconds. T equals 12 seconds. So how in the world do we find what the speed is at that individual point? We're going to do the exact same thing, but we're going to use a tangent line. And it's going to require a little bit of estimation. So I'm going to zoom way in here. We're trying to find the slope at that point. What's not really curving a whole lot at that point, what if we just sort of extend down to here and then maybe up to like right there and use those 2 endpoints to get a pretty good approximation of what the slope is at that point, okay? So if I were to zoom back out, let's see what this looks like. It looks like we're going from -4 up to +4. So our displacement is 8. We're going 8 meters in some period of time, which is a little bit hard to determine, right? How many seconds is like this? I don't know. Like 0.15, maybe 0.2, and then the same amount on the other side. It could be like 0.4, maybe 0.3 seconds. It's an estimate. That's the best we can do with the data that we have. So I'm going to say that maybe this difference is 0.3 to 0.4 seconds. I don't know what the range is in the homework. They have to have a pretty broad range of accepted answers because you can only do what you can do with the data you have. So I'm going to go ahead and just say that our answer for this part, V is going to be delta x over delta t is 8 over, like, let's just call it 0.35 and see what that gives us, okay? And I don't know what that number is, and I don't really care, so I'll just let you do that. There we go. K and L are the same. It's now asking when it's moving in the backward direction with the fastest speed. So now I'm looking for negative slopes, and I want the steepest negative slope. Well, it's only negative between 6 and 10. Where is it the steepest between 6 and 10? I would say at 8. Before that, it's sort of flattening this way, and after that, it's flattening the other way. Okay, so at 8 seconds, I would say it is the steepest, so t equals 8 seconds. And we would have to do the same sort of thing at this point, and I already sort of drew the line there. Pick a couple of endpoints and try to estimate what that time difference is as it goes from -4 or from +4 to -4. Okay? Same idea. As it increasingly gets hotter in here, did someone turn the heat on or something? If there's someone in the hall that's trying to like sweat us out of here because they really want the room.
I think it has to do with the humidity outside.
The humidity outside plus all of you, like being alive, are generating heat. If you could just die for a few minutes, we could cool the room off some and go from there. All right? Does anyone have any questions? Hey, it's not all the way to cooler. There we go. I turned it a little bit. Can I twist it more negative? It's a little better out there, but not much. Does anybody have any questions about this problem before we move to one more for the day? Yes.
So for J, is that really how you do it?
You would have to find the slope between these 2 points that I drew over here. For J, sorry. That's what we have there. Okay.
So if you divide 8 by that number, it should be the same answer.
That should be the correct answer. Yep. Yes.
Are you okay? So I hate that for one.
You hate that?
I hate that a lot because I was like
Aw.
trying to take like the 2 seconds and then I guess I don't know.
Yeah,
But
maybe
would
a
you
broader
give-
range.
Yeah, would you give us a problem like that? Like where you have to estimate like that?
I wouldn't make it that hard to estimate. And even if I did, I would accept quite a few answers as long as it looked like you knew what you were doing. Because I'm not a computer. I can sort of judge whether it looks like you know what you're doing or not. Yeah.
Are you skipping through M and N?
M and N. I should say something about M and N. M and N. M and M is better. M and M's. Which color of M and M's? I don't think it matters. So, at what time does the acceleration have the greatest magnitude? Acceleration means velocity is changing. When is the velocity changing the most? When is the slope changing the most? Is what this is asking. See the way we step through those things? Acceleration is changing velocity. Velocity here is represented by the slope. So where is, or we should say when, is the slope changing the fastest? When is the slope changing the fastest? Greetings. The aliens have arrived. One day maybe that'll be what that means. It'll probably be hostile. It'll be terrible. So when is the slope changing the most? We're just going to have to look at some different periods of time and see. The aliens have arrived. Please stay in the building. Yeah, we understand. So if I just look between these two things, like the slope changes from this to like this. It didn't change a whole lot. In this range, it's not changing at all. It's just constant. Here it like changes from almost flat to flat. Here it changes from flat to pretty steep. There's a pretty big change in this time range here. And then it's not changing very much there. And then, ooh, it's changing from steep to flat. And then back to steep. But steep in the opposite direction. It's changing a lot between 9 and 11 seconds. And then over here, it's relatively constant. I would say that the most amount of change happens here, and the middle of that is the 10-second mark. Okay? It is changing rapidly at that point. So let's put that in. T equals 10 seconds. And then the last question is, ignoring the starting and ending times, when is the acceleration nearly zero? Well, that would be asking when the slope is constant, when it's not really changing at all. So looking back at our diagram, where is the line basically constant? Well, 3 seconds and 8 seconds. It's almost a straight line at those 2 points, okay? So there's not much acceleration there at all. So t equals 3 and 8 seconds. Whew, good times, right? So at t equals 3 and at t equals 8. At those 2 points, there's not much change in the slope. Yeah.
So if we're looking at the position versus time graph, and acceleration was the second derivative, how position would that be the average of the whole graph?
You could think of it that way. If you're comfortable thinking through those derivatives and what the curve would look like, that's totally fine. That works. Anybody else? You should all come right here. Feels pretty good right here, nowhere else in the whole room. So everybody join me over at the side. How are we doing on time? We still got a little bit more. Let me jump over to this other problem, and I'm going to get it started, but I'm definitely not going to finish it. But I want to at least do this first part, and then we're going to quit even if time's not up, because melting. Okay? So, it says we have a coyote and a roadrunner, harkening back to what is now an ancient cartoon that probably none of you have ever seen. Yes, no? You have? Okay, you go back and watch old cartoons, good. So let's see. The coyote has acquired a set of jet-powered roller skates, fantastic, which provide a constant horizontal acceleration of 19 meters per second squared. So he's going to go faster and faster and faster and faster and faster. The coyote starts from rest, 70 meters from the edge, at the instant the roadrunner runs by in the direction of the cliff. So I'm going to start by doing my own diagram because they haven't given them enough room before they get to the cliff. So let's say that this is x equals 0 and call that the positive x direction, which would make this positive 70, and that is where the cliff is. I'm going to say that the coyote, we'll put a little c in there for coyote, is at rest. And at this same point, the roadrunner zips right on by with some velocity. Okay? We have two objects. They're doing two different things. Notice part A asks about the constant speed of the roadrunner. They really should have stated up in the statement of the problem that the roadrunner runs by a constant speed, but they didn't. So alas, what are you going to do? So we could say, first of all, let's go over here somewhere. The roadrunner is moving at a constant velocity, and the coyote is not. So I'm not going to put anything there. And I'm going to list out the variables and see what we know. Okay? If you are presented with a problem that confuses you like this, the exam comes, and you see things are moving around, and you're like, and you're actually making those sounds, step back from it for a second. Don't worry about what it's asking down there. I haven't even, it says something about a constant speed. It's going to ask us something. I don't care, all right? Draw a diagram, set the origin in the positive direction. You should be able to do that for anything, okay? And then make a list of variables. You know what the motion variables are. If something is accelerating like the coyote, there are 2 positions, 2 velocities, acceleration, and time. Always, 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 always. Position, velocity, acceleration, time. Position, velocity, acceleration, time. Okay? If something is moving with constant velocity, like we had something in free fall that wasn't accelerating sideways, there are only 4 variables. 2 positions, where did it start and where did it end up, whatever that constant velocity is, and time. Even if you fill nothing else in at this point, I will give you points on the exam. So, we haven't done anything related to the problem, really, at this point. Show your work, do what you can, all right? You may find if you get this far and start plugging numbers in, all of a sudden you're like, hey, I have some equations, and you throw them in there and start doing stuff. Next thing you know, you have answers and you surprise yourself, okay? Question?
So, we don't have velocity, the final velocity and no acceleration because it's a constant velocity.
Let's see. We don't have a final velocity for the Roadrunner because it's just the same the whole time. So just saying velocity is good. And acceleration is 0, so there's no real point. Okay? So what's the starting and ending position of the Roadrunner? 0 and 70. Question?
Wait, VIX squared, what's the velocity initial x squared?
Squared?
Yeah.
No squared. Equal signs.
Oh.
Sorry. I know. We need bigger screens, smaller classrooms, something.
Why do we
So.
have velocity initial and velocity initial x?
Say again?
Why do we have, oh, that's y initial, right? Under C?
Under C,
Yeah,
we have x initial,
right.
x final, velocity initial x, and velocity final x.
Oh,
All for the coyote.
I thought there was like a 2x initial.
I'm sorry. I can't write. I'm causing all kinds of problems. Where does the coyote start and finish? I would agree with that. So he's going to fly off the cliff, but we're going to temporarily stop the problem at the cliff until we get to part 2. Okay, so we'll say initial is here and final is there. They're both 0 to 70. Okay, the velocity of the Roadrunner, it turns out that is what we're looking for, like right down here. See, constant speed for the Roadrunner. We'd like to find that. And we don't know how long it takes for the Roadrunner to run from that location to the other location. So question mark. Both of those are questions. In the case of the coyote, it said that he started from rest, so that's 0 for that starting velocity. We don't know how fast he ends up running. They told us an acceleration, and we don't have the time. Yay! You drew a diagram, you put in origin and positive direction, you listed as many variables as we had, including what the unknowns are. You just got some points on the problem, even if you do nothing else, okay? But let's think about what it's asking us to find and how we could get there. If I want to find how fast the Roadrunner is going, specifically to get to the cliff before the coyote gets there, okay? So imagine Roadrunner runs by, and then the coyote starts. Right, it's going to take some time for the coyote to get up to speed and eventually to the cliff. However much time that is, that's how much time the Roadrunner has. Agreed? The amount of time it takes the coyote to get to the cliff is how much time the Roadrunner has to get there to have a chance of getting there before. Okay, so if I can find this time and then put it over there, I know how much time the Roadrunner has to run the 70 meters. And then I can find that velocity, okay? We are going to do that on Thursday. So we will finish up that problem. If you want to take this and run with it, just like the coyote or the roadrunner, be my guest, see how far you get, and then we'll finish it up for you on Thursday. Goodbye. Study hard. No exam. I'll send out an announcement. It's on Tuesday.